Assalamualaikum warahmatullahi wabarakatuh, and good morning to Dr. Ernie and my beloved friends. My name is Emilia Asmara binti Mak Daud, and my team members are Muhammad Nurazan bin Muhammad Hamdan and also Muhammad Akif bin Hussein. In this video, we will present about a copper zinc oxide based catalyst for methanol production. I will start first with the history of methanol. In ancient Egypt, the methanol is being obtained from the pyrolysis of wood, which is used for embalming mummies. Then, in 1661, the ethanol was isolated by Robert Boyle and analyzed by Jean-Baptiste Dumas and Eugene Peligot in 1834. But during 1923, the production was started to industrialize by Alwin Matech and Matthias Speer, working at BASF. And today, more than 19 methanol plants span the entire globe with a production capacity around 110 megatons. The demand is 40% for emerging energy application and 10% for the chemical feedstock. Nowadays, the catalysts for manufacturing methanol are based on copper zinc oxide heteronanostructure supported by aluminium oxide. The picture shown here is the structure of copper zinc oxide. As you can see, the zinc oxide active phase should be completely covered the copper sized particle to avoid the carbon monoxide formation, which is unwanted product, to make the catalyst highly selective toward the methanol production. Now, we will move on to the properties of copper zinc oxide based catalyst. First of all, zinc oxide is classified as heterogeneous catalyst, in which the catalyst and reactant are in different phases. Next, the catalyst undergo a very high performance level under relevant industrial condition, for example, at a pressure of 50 to 100 bar and temperature between 220 to 300 degrees Celsius. Hence, one may rationally assume that the catalyst is highly active for the direct carbon dioxide hydrogenation to methanol. Moreover, under normal operating condition, the catalyst copper zinc oxide has a long lifetime of a few years. However, it is very sensitive to sulfur poisoning, so that sulfur content in the feed stream are reduced less than 0.5 ppm. And then, zinc oxide acts not only as dispersant and stabilizer, but also reported to cause a synergetic effect. And lastly, it also provides the active centers due to the interface contact with the copper phase, which result in a beneficial electronic structure for absorption of reactant and product. Hence, the activity of copper zinc oxide is several magnitude higher than the individual copper or zinc oxide.
For the next part, we will take a look at the production method of methanol, which specifically at the BASF process. This process involves hydrogenation of carbon monoxide with iron-based catalyst at 500 degrees Celsius and a high pressure, which is 100 bar, to produce methanol. Okay, then they tried to use waste gas from ammonia production to replace carbon monoxide. This will produce methanol along with other byproducts. The problem that arises from this new process is, one, the process thermodynamically favored the byproducts instead of the methanol. Then the pollutants in the precursor gas, which is the waste gas from ammonia production, deactivate the iron-based catalyst, which in turn, the carbon monoxide and the iron cannot react. Therefore, there are no penta-coordinate complex form. Okay. So the solution for this problem is to use oxide and metal-based catalyst. For example, the zinc oxide and Cr2O3 and zinc oxide and copper oxide. Then for the zinc oxide and copper based catalyst, it is a mixture between copper and zinc oxide which creates small aggregates. Zinc oxide is aggregated around copper, which can be seen in this diagram here. This core shell structure is responsible for the selectivity of methanol production. The ZNOx represents the outermost layer of the shell where the oxygen vacancies are located. The morphostructural arrangement of the aggregate plays an important role in the selectivity towards methanol instead of the other byproducts. In this structure, hydrogen and carbon dioxide are chemisorphed on different surface of the catalyst. So, hydrogen is weakly adsorbed on the surface of copper, while carbon dioxide on the surface of zinc oxide and ZNOx. Okay, copper is metallic, therefore it is able to rapidly dissociate and recombine hydrogen. The weakly adsorbed hydrogen then was put to both other surfaces. If it is put to ZNOx, it will form methanol, and if put over zinc oxide, it will form carbon monoxide. Okay, this diagram right here shows us the process of the chemisorption, the reaction, and the products that will get from the reaction.
I will continue with the current technology related to the methanol production industry. So, here there are three of them, which are: first is the synthesis from syngas, second, through carbon dioxide hydrogenation, and lastly, from the photoreduction of the carbon dioxide, CO2. So, for the first part, which is the synthesis from the syngas, there are three stages that involve in the process, which are synthesis gas production, syngas conversion into crude methanol, and lastly, the crude methanol distillation to reach the required purity of the product. The steam and autothermal reforming, which is SMR and AMR, are needed to generate the syngas mixture. Next, for the synthesis through the carbon dioxide hydrogenation is carried out from 35 to 55 bar of pressure and at temperature of 200 degrees Celsius, while the catalysts are based on the copper zinc oxide supported by aluminium trioxide. It is advantageous not only for the exploitation of non-fossil fuel sources, but also because it overcomes the carbon dioxide sequestration, which is a very costly process, and also mitigating the greenhouse gases effect. Lastly, for the last technology is the synthesis from the photoreduction of the carbon dioxide. For your information, it employs the principle of photosynthesis in plant, in which plants will absorb the carbon dioxide together with the sunlight and water to produce the carbohydrate energy for themselves and also oxygen as the byproduct. The water will serve as the hydrogen sources for this technique. Next, for the uses of methanol, or can we call the methanol consumption in the world. So, based on this pie chart, most of the methanol produced in the industry will be used in formaldehyde production, which cover the 30% of the consumption. Other than that, methanol are also used in the production of other chemicals, which are 2% for dimethyl terephthalate DMT used for psychedelic drug, 10% for acetic acid that can manufacture many more applications, 19% for the methyl third butyl ether or MTBE that used as additive in gasoline, 3% of methyl methacrylate that always involved in manufacturing of resin or the polymer, 8% for gasoline and fuel for the transportation uses, 4% for dimethyl ether or DME that used as fuel in household and industry, and lastly, 24% of other applications that have not informed before. Next, let's jump to the conclusion of our presentation. First, methanol was firstly industrialized by Alwin Mistach and Matthias Bayer, working at BASF. Next, current technology in methanol production chemistry are involved synthesis from syngas, photo reduction of carbon dioxide, and lastly through the carbon dioxide hydrogenation. The third one is the highest methanol consumption goes to the production of formaldehyde, followed by the others chemical. So that's all from us. Thank you.